So hi, I'm Shivay. I'm a developer advocate at Millisearch, and I've also been a contributor to Kubeflow.
Hello, I'm Rishit. I'm an undergraduate student and a researcher at the University of Toronto, and I work with academic machine learning research. I've also been a contributor to various open source projects, including Kubeflow, PyTorch, and more.
All right, so of course, some of you who might be aware with machine learning might be aware with the typical machine learning lifecycle and pipelines, so I'll not go too deep into it, but primarily whenever you're dealing with any machine learning workflow, you'll start with data collection, you'll have the machine learning code itself, which usually is the smallest part of the entire pipeline, and once you have trained and fine-tuned your model, it goes into production, and of course, as part of the production process, you'll be having a lot of serving infrastructure that will be used to go ahead and launch your model, and then of course that will involve a lot of CPUs, GPUs, depending on the size of the model. Especially today, when we're looking at large language models, you require a complex complex architecture of involving multiple GPUs or multiple TPUs at the same time. And then of course, once the model goes into production, you'll also be handling monitoring. So as you see that since there are so many different components to this machine learning pipeline, it can be very complex when you're setting this up for the first time. And primarily, I like to divide them into 4 different bits. So of course, starting with the version control. So whenever you're dealing with a lot of data, this data set can be very destructured, and there may be a lot of complexities, especially dealing with removing a lot of the different issues that the data might have. So the data cleaning process itself takes a lot of time. And especially when you have to label this data, especially if you're having very large data sets, there will be a lot of heterogeneous data as well. So data labeling itself is a very huge challenge that you have to solve as one of the generally the first steps in the entire machine learning pipeline. Then, of course, coming to the model training and fine-tuning. So as a data scientist or machine learning engineer, one of the biggest tasks is to fine-tune the model so that it can fit perfectly with what you're training it on. And then, of course, to expect it to give good results at the end once you have launched the machine learning or it's about to be launched into production. Now, once the model is fine-tuned enough, the next big thing is to deploy it, right? And especially for some of the larger models that we're looking at today, deployment strategies have changed drastically. Whereas with some of the small models, you could run them on a single CPU. Today, you require strategies where you might need to run them on multiple GPUs. And of course, like me and Rishit, I gave a talk at KubeCon regarding how you can effectively use multiple GPU strategies. So feel free to interact with us if you want to learn more about that. But of course, today, scaling up your machine learning models has become a lot more complex. And tools, especially like Kubeflow or Flight, require special configuration that you might need to provision in order to have multiple GPUs working in together to be able to run some of these larger models. So things like data parallelism, model parallelism are adding more complexity to this entire deployment. And finally, when it comes to monitoring, so of course, once the model goes into production, typically the models degrade over time as you use them in production. So having to always closely monitor the performance of the models in production is also very important. And you have to, of course, maintain these models, have to continuously update the models as the data set changes, of course, and the nature of the model in production changes. So in ensuring consistency and reliability of these models in production takes up a lot of time. So what we'll see is that how GitOps principles can allow you to make some of these things, especially things like data versioning, infrastructure provisioning, and changes in your manifest files when your model is in production, how GitOps can actually help that. And Rishit will walk through some of these benefits of using GitOps.
Sure. So let's get right onto it. And this is a very deceiving title. Machine learning loves GitOps. We want that, but let's change this to, well, sometimes. And I'll also start by saying I don't use any GitOps principles in most of my academic machine learning research. Okay, I'll be honest, in all of my academic research. But why don't I do it? If this talk is centered around machine learning loves GitOps, why don't I do it? And well, because at the heart of GitOps, patches need to be declarative. And in a lot of academic scenarios, that just isn't possible. That just isn't possible for most academic scenarios. But both of us also use GitOps in the machine learning development workflow. So let's start by walking through an example, and we'll take a look at a couple of these examples. to see how it can be used efficiently in some parts of the development workflow. So, okay, the experiment I have at the moment is I'm trying to train a simple ResNet model, and I want to do this on the tiny ImageNet dataset, which is 100,000 images, and I have a few GPUs doing this stuff. So this is the experiment we have set up. And ideally, while the model development part, you want to make a hypothesis. So I start by making a hypothesis that I update the batch size to be larger, because a larger batch size almost always gives you better model performance, almost always. So because we can handle it, I make this patch. I think a larger batch size might improve it. And this is what my change looks like for the repository, just a declarative change out there. So I simply update the batch size, and so the key thing to note over here is that the hypothesis I make is declarative, and I make it as a pull request, at least for this example, so it's versioned and immutable. Starts sounding a bit like I can use some of the GitOps principles now that my patches are declaratively put in. So I say we can now probably go on to the pull and reconcile part. So what I now do is I see how does this affect the model performance, and that's where the pull and reconcile part comes in. And I see a report, at least for the experiment we have over here. And what I also do is I store and compare multiple experiments. So this is the experiment I ran yesterday. So I took quite some compute power, and I trained 100 models on tiny ImageNet with the GitOps workflow I was just talking about. And that did make it a lot easier for me, training those 100 models, comparing them out. So this is TensorBoard. So a lot of the comparisons happen in TensorBoard, but orchestrating all of these 100 training jobs, making them in such a way that all of these are well versioned. I can see this part impacts my whole training job in this way, and I finally get it as a beautiful TensorBoard report. So that's what, in this report, that's the link that we get, a TensorBoard link, and all of the runs are added to the TensorBoard link. So this seems pretty interesting for our use case, because you are now able to easily do some of the parts we wanted to do while the modeling process. And by the way, just as a side note, I wasn't trying to get a pretty good model performance, but using this kind of workflow actually allowed me to do pretty well on tiny ImageNet. So infrastructure provisioning. So this also declaratively provisions infrastructure, and a lot of it, for this example at least, is taken from Keras.io, and they have a beautiful guide on it. We also have a talk about this at KubeCon, so I won't go into provisioning infrastructure or declaratively doing that. But finally, what I want to do is the GitOps loop. So I take a look at all of these TensorBoard experiments, TensorBoard comparisons across multiple different runs, and I say this model in this patch looks good. It satisfies all things I want to do, and then I just promote it, and there you have it. So by the way, all of this is open source, you can try it out. So these are with tiny ImageNet. Of course, you can make it work for anything you want. And this also brings me to this interesting, to this really apt image from CodeFresh, and this talks about the entire GitOps loop. And this might sound very familiar to most of you, since it's CDCon plus GitOpsCon. And this is pretty similar to your usual process while modeling machine learning algorithms. And with a few changes, you can start leveraging the powers of GitOps and the powers of all the GitOps principles. like one of the examples I just showed. So, so we'll also talk about a few more silos inside the machine learning workflow, where we have been able to use and implement GitOps pretty effectively. So yes, you can do a lot more inside the machine learning development workflow with GitOps. And Shivay will talk a bit about data versioning, which we didn't really talk about in this experiment.
Yep. So just as a side note, DVC, it's called data version control, and this is a tool that allows you to very easily manipulate both your data and model. So of course, as we might know that when you are dealing with machine learning, especially in that fine-tuning phase, you might have to run a lot of different experiments with different set of models, with different set of model parameters, or different data sets as well. And as you kind of fine-tune this model, because you have to maintain all these changes, you also want to ensure that you can very effectively track these changes with your experimentation. So in order to make machine learning model experimentation easier, and so that you can very easily manage your model and data, so both data versioning and your model versioning can be done very easily with the help of DVC. So it's an open source tool. So this of course directly uses the principle of GitOps, where we are essentially looking at the different versions of code. That's a very standard principle that's employed by Git. So over here, what I've done is that you can see that I just ran a very quick experiment, and of course, like because with the time constraint, I ran it over an MNIST dataset. It's a very simple machine learning model. And if you look over here, that I've actually done DVC experiment show, which basically keeps a track of all the different experiments that you have run. And you can take a look at when that experiment is run, and you can very effectively or efficiently just change between these experiments. And each and every experiment, as you run it and you log it with the help of DVC, it will keep a track of all the different model changes that you have done, and also the changes in the dataset that you have actually done. So you have dedicated commands that are very fine in tune with, similar to how Git works. So for example, if you do DVC add, that basically helps you to keep a track of your data changes and your model changes, similar to how we use Git add, right? And then you can use DVC checkout to change between these different experiments, similar to how you do Git checkout to go between different branches. And here's another example where I've basically been able to do 2 different Git commits, and I had logged one model under one different commit, which again was a separate experiment, and again I had a second different model with more number of images. So I basically changed my number of images, and I can very easily track this with the help of DVC and with the help of Git. So of course, that's one aspect of being able to use GitOps principles directly in the realm of machine learning with the help of DVC. But over to Rishit to take a look at some of the other aspects with the help of Kubeflow.
Sure. So, well, most of what we have been talking about, at least my demo, was at least the infrastructure provisioning for the quick experiment we saw, was Kubernetes clusters, uses Argo CD in the backend, and I just wanted to show you how the GitOps things work together. But GitOps is more than that. You can most certainly use anything. Just makes it easier for a demo, and it's also what I use. But another thing which I wanted to quickly demonstrate, and we are almost at time, so I'll make this quick, is so I have Kubeflow over here. So all of these are customized directories for installing Kubeflow, and another thing which is pretty common is probably having custom Kubeflow components. So you would probably make some changes over here. One of the changes I've made is I'm now using MetalLB for the networking parts, and so this is one of the changes I make. And think about this as adding a new custom component to Kubeflow, and so with GitOps, and let's just do it out ourselves. So this is also set up to a GitHub repository, and I do have GitHub Actions doing it. And essentially, the idea of showing this is how easy it is to make use of GitOps principles to deploy Kubeflow. And I'll actually try doing that with Argo. So at the moment, because all of it is configured to my GitHub repository as well. You can also feel free to check this out. This is for the latest Kubeflow release, and yeah, I can just start doing that, and it will fetch the head and start provisioning the resources. We are already at time, and I see a stop sign, but you should see all of these in Argo CD UI, which is pretty straightforward. But essentially, there you have it. Any new Kubeflow component you add or customize, that's right out of the way deployed for you. The patch is applied, it's and Kubeflow is being deployed. So this Kubeflow deployment will take around 30 to 45 minutes. So, but yeah, you'll see this up on Argo CD UI, all these resources being deployed, and essentially you can also make use of GitOps powers. So that's it for the talk. Thank you. I'm Rishit.
And I'm Shivay, so we are open to any questions if we have time.